Welcome back to DeepRob for lecture 4. Today we're going to be talking about regularization and optimization. So now this is getting into how it is we can train our neural network models and our machine learning models from the data that we have as input. And before we get started with kind of the core of today's lecture, just a few administrative updates. So first, Project 1 reminder. So Project 1 was released last Thursday, actually last Friday morning. It's due Thursday, January 26th, so still quite a bit of time to work on it, but definitely suggest getting started sooner than later. All the instructions are on the website. The autograder is now online, so everyone should be able to submit to the autograder. If you're having any issues with that, just let me know. In addition, we looked last week on Friday at the data set that we're going to be using for Project 1. So in particular, this props data set. So we have 10 classes. They're common household objects, and we're going to be trying to categorize each image that we see from a test set based on our models that are trained from a training set. So if you're curious about where this data comes from, we had a really good discussion on last Friday about the tool that was used to create this data set. So if you're interested in this data set, I'd recommend maybe going back and looking at those slides or the recording from last Friday, and then feel free to post questions on EdStem or come to office hours to talk more about this if you're interested. I'll just also mention this is like an ongoing research project. So this is a paper from less than, I think it's just over maybe a year ago. So if you're interested in this as like future directions for research, also feel free to reach out to the authors that were on this paper, and they'd be happy to discuss that. And then one final note for the quizzes, we brought up last week the quiz policy in lecture, and then we made a slight change based on our collaborating institution of University of Minnesota. So what we decided on is to have, in order essentially so that you guys are not stressing about quizzes during lecture, we'll have the quizzes be released 7 a.m. the morning of a quiz day. So it'll be like the same day as lecture, and then they'll be available up until the start of lecture time, so 3 p.m. Eastern. Today is the first day of the quiz, so there is a quiz released on Gradescope. If everyone in the class, either on the waitlist or who's enrolled, should be able to access the quiz, but I'm anticipating that somehow there's maybe a few people that were somehow like not synced with the roster. So what we've done just for today is made the quiz 1 available until 6 p.m. Because I looked just before lecture, and I think it was like roughly 50% of students have taken the quiz. So you still have, 3 hours roughly left to take the quiz. It's a 1-question quiz, should be fairly short, based on our past lecture discussions. So if you are not able to access it right after lecture, please come up and see me, and I'll make sure that we get you added. But it seems like people are able to access it so far. And yeah, and once you open the quiz, there's a 15-minute time limit, FYI. Okay, before we get into the material, I'll just pause and see if there's any administrative questions that people have that I can answer. Okay, not seeing any, so we'll get into the material. So just as a brief recap, so what we looked at in last lecture was this set of linear classifiers, right? So we looked at like an SVM loss. We do have a question. Okay, what resources are allowed to be used during the quiz? So we have not spelled that out on the syllabus, actually. That's a great question. You're able to use OpenNote on the quiz, so these are really conceptual questions. These are not questions that would be like that you would memorize directly from lecture content or from projects. We're not asking implementation details, so you don't have to write like compilable code on the quizzes. So if you want to use OpenNotes from your lectures or like go back to the recordings, that's okay. Yep. So these are new conceptual questions to get you thinking about the material and to gauge where you are with the understanding of the concepts. We'll add that to the syllabus also. Okay, so last week on Thursday, we started looking at a set of linear classifiers, right? So we looked at a few different viewpoints by which we could try to understand these classifiers, right? So we saw how if we try to represent a parametric function as a set of linear equations, we could try and train then potentially a model using different loss functions, or we could at least describe which of these models was either desirable or less desirable based on a set of loss functions. And so these loss functions we looked at, so for example, like the softmax loss and the SVM loss, so these are what you're starting to work on implementing for Project 1. And where we left off was with this question, given that we have some linear classifier, so some function of, let's say, an input image and the model parameters W and B, how do we actually find a good set of parameters, W and B, that would actually like correspond to a model that's performing well at our image classification task, right? So what we ended up kind of deciding was that it's not enough just to define a loss function. We also need some way to start to optimize that loss function so that our models start to improve and learn from the data. And one issue, though, that we didn't bring up, which is a common problem throughout really all machine learning, but also deep learning, is the idea that a loss function, in the way that we've discussed it up to this point, is really only describing the performance of our model on the training set, right? So we were only taking the sort of the sum total loss or the average loss over the training examples. But really what we would want to care about is how the model is going to perform once we deploy it onto a robot, and then that robot goes out into the wild and starts using the model. And so there's this sort of discrepancy between how we've defined the loss function and then maybe ultimately how we see our model being used in the real world. And so this gets into some questions about how it is we're going to set up optimization in a way that would allow our model to perform well on the training set, but hopefully also the testing set or the data that it's going to see after training. And so these two topics together, so like optimization in terms of how it is we're going to train the model, but then also regularization, which is how we can hopefully ensure that the model performs as well on the test set as it does on the training set, is the topic for today's lecture. And so to start with, let's kind of dig a little bit deeper into that idea that our model might not perform as well on the test set as it does on the training set by looking at this idea of overfitting. So this is a very common topic within machine learning. And the core idea is if we have some model that performs very well on the training set, but then we go and evaluate how it performs on the testing set, which is unseen data during training, and we find that it has poor performance on that unseen data, that would be a model that we would consider overfit. So it's overfit to the training data set we would consider. And so to look at this as like with a concrete example, let's say that we have a linear classifier which has a one-dimensional input. So you can see this function, so that's producing the score S sub I as a function of our single one-dimensional parameter W sub I, and then our input one-dimensional data element X plus some bias term. So there's the scores. And then let's say that we set up our our loss function according to the softmax loss, which we looked at in last lecture. So we're going to take the score corresponding to, let's say there's two possible classes. So let's say class 1 and class 2. We'll convert the score into a probability using the normalization function that we looked at last time, and then we'll define our loss function as a softmax loss. And let's consider a set of possible models that we could potentially have trained from some training data and consider which of them might be overfit or not. So in these plots, so the thing to sort of, the way to understand these plots, so the x dimension, so this horizontal dimension, that's the input data that our model is going to take in and try and use to decide which category from either class 1 or class 2 an individual data element belongs to. Let's say then that the points along that dimension, which are either green points or red points, those are our training set. So that's the data that our model has been used to actually to try and learn how to predict new unseen examples. And then the two curved lines in each of these plots, so the orange line and the blue line, those correspond to the scores, or actually the probabilities that are produced based on the individual input along the horizontal axis. So the vertical axis of those lines corresponds to a predicted probability conditioned on the input falling somewhere along the horizontal axis. And so the way then to sort of understand these is that whichever of the two lines has a higher y-dimensional value would correspond to the class that our model is predicting. And so the two separate figures then that we have would be if we imagine training two separate models on these same set of training examples, and potentially we would get different models. So potentially this example on the right, you can see has essentially is predicting higher scores for the two classes nearer to the origin of x equals 0, whereas the model on the left has lower scores in that for each of the two classes in that region. But if we consider our loss function, the softmax loss, even though these two models are different, so the parameters, so the individual weight and biases of these two models are different, both of them have perfect accuracy on the training data. So they have a different loss, they result in a different loss based on these training examples, but they both have perfect accuracy. And so one reason, though, that we might want to be a little bit skeptical of this this like observation is we could imagine like yet another model being trained on these same points that has even more extreme cliffs in its sort of decision boundaries, but yet again having perfect accuracy. And so the reason that this is somewhat suspicious is that these fairly different models in terms of where their decision boundaries are, all having the same accuracy, might be an indicator that some of the models are overfitting to the training data set. And the reason that we might want to think that is because if we look within these regions where there's this very steep cliff in the decision boundaries, there is actually no training data in that region. So each of these different models is deciding how it's going to be predicting unseen data elements given this region of space where it didn't have any training examples. And so this is a potential source of overfitting, and it's an indicator that potentially, like the model on the far right, it might not generalize well to new data where it's possible that there's a different pattern within this region of space that didn't have any training examples. And so if we want our models to generalize well, regularization is a tool that we can use to try and force them to sort of perform well on regions of space within the input space that was not seen during training. That's the goal of regularization. So if we want to try and move beyond the training error, we can introduce like a regularization term to our loss. So let's say that we have our loss function, which we've discussed in the last lecture. So this is the average of some loss function L sub I over all the individual examples in our training set from example 1 up to example n. We could consider this portion of our overall loss function, we'll say the data loss. So this is what's going to incentivize our models or sort of reward the models that predict very accurately on the training examples. And we could then introduce a second term to our overall loss function, which is called a regularization term. And so the goal for this regularization term is going to be to prevent our models from doing sort of too well on the training data at the expense potentially of performing poorly on the unseen test data. And so you can see one very big difference between the data loss term and the regularization term is that the data loss term is a function of our training data x, whereas the regularization term doesn't consider x in its metric. So it just considers the parameters of our model w. And so this lambda then, if you're curious, that's a hyperparameter which we could tune. So we could sort of decide how much emphasis we want to put on regularization versus the data loss term. So this is the direction that regularization goes towards, which is sort of, you can think about it as like augmenting our loss that we've been talking about with this additional term to try and incentivize models to not fit too well to the training data. And so some common examples, some relatively, we could say like simple examples of regularization would be L2 regularization, where this R term is simply the sum of the square of all of the elements within our parameter set. But then also L1 regularization, where we take the sum over all of the absolute values of the terms within our parameter set. And so these are two common examples, but what we're going to look at kind of in future lectures will get more complex. So when we start looking at neural networks and convolutional neural networks, there will be topics like dropout, batch normalization, like stochastic sampling of the training set. All of these things will come up in future lectures as ways that we could augment even further this idea of regularization during the training of our models to avoid overfitting. So so if we kind of go back to our simple example, let's see, we have a question. What is the typical value for this hyperparameter lambda? So that's very dependent on a number of variables. So it's dependent on the model that you're choosing. So in the case of linear classifiers, you might want to choose a lambda that's very different than in the case of like convolutional neural networks. But also that depends on the specific data set that you're using. And so if you're like in more complex data sets, it might be where you have like a very small amount of training data in comparison to the size of test data. You might need to increase the regularization term to try to avoid overfitting to those small number of samples that you have. So it really depends. So in practice, typically what's done is we treat that truly as a hyperparameter where you'll try many different values, and then through cross-validation, you'll hopefully settle on some amount of regularization such that you're still getting good fit to the training data, but you're not hopefully overfitting so that you have some confidence that when it is deployed on test data, it'll perform well. Because that's a great point, is that if you have too strong of a regularization term, it's possible that you could sacrifice your actual ability to fit to the data in the first place. So that would be a case where we would actually call it underfitting. Like your model is too simple to actually fit to some complex patterns in the training data set in the first place. Yeah, another question? Okay, so yeah, so the question was if you, so let me see if I caught that right. So the question was, if your training data set is infinitely large, do you not need regularization because you could in theory learn like a universal approximator? As a general rule of thumb, like when you're approaching in practice, I think that's reasonable. On the theoretical side, I think it's more complex because like the specific distributions of the data set, even though it might be very large, can affect like a specific model's ability to overfit. Yeah, so the question was, as a general rule, can we take it that the larger the data set, the less regularization we need? And I think from a practitioner standpoint, not a theoretician's standpoint, I would say that like as a general rule, that's probably okay to approach, but if you were wanting to have like concrete theoretical guarantees, I don't think we can say anything concrete because it depends on the distribution of data that we're trying to fit to. Can I say something about the distribution of the data?
I'll just say, the more data you have doesn't necessarily mean you will get covered areas of space that you'll need to avoid overfitting. Gotcha. So it's both the distribution and the quantity.
Right. So yeah. So to repeat that for online. So then like a kind of scenario came up. Like imagine that we are trying to classify the coffee mug from our data set, but maybe in our maybe we have millions of examples of the coffee mugs. We have like a lot of data, but they're all maybe oriented in a specific portion of the image, or they're all oriented in space in the same way. Even though we have many examples of that, because we're not covering the full distribution of possible poses where we might want to detect the mug, you can still overfit even kind of regardless maybe of your regularization term being small, despite the fact you have many examples. Yeah. Thanks for the questions. Okay, so regularization at a high level, the idea is that it's going to be preferring simpler models, right? So it's sort of encouraging the models to not get overly specialized on the specific training examples that we're giving it to learn from. So let's consider how this simple L2 regularization could be used in the 1D example that we looked at on the past few slides, and what effect this L2 regularization term will have when we're training these classifiers. So what that would look like is we have our softmax loss, which we had been considering, and what we've done is we've added the regularization term, right? So we've added this lambda and then a sum over all of the parameters w sub I in our W matrix, and then we're just squaring each of those individually within the summation. So this regularization term, what it's going to do is it's going to cause the loss to increase for any of the models that have those really sharp cliffs. And the reason why, so the sort of geometric interpretation that we can do in this 1D case is that for the models that have this sharper cliff, so on the right-hand side, and to some extent the middle model, the sharper cliff corresponds to like just a larger W sub I term, right? Because that's just the slope of the scores that our model is producing. So the steeper the slope, that's going to correspond to these more sharp cliffs. And so if we imagine like these W sub I's for the steeper cliffs, like steeper slopes, those terms are going to contribute positively to the loss. And so correspondingly, the loss for these models with the steeper cliff are now much larger than the overall loss for the model that has the less steep cliff. So adding this L2 regularization is encouraging models that are simpler from the standpoint of their weights. Like it's a less extreme decision boundary being encouraged or preferred. So to look at that, like also more concretely, we could actually try and work through for a set of weight matrices what this L2 regularization term will actually look like. So let's say that we have, instead of a one-dimensional linear classifier, let's say that we have some linear classifier that has 4 dimensions as input. So we've got like maybe one example input here, this x vector, which is all ones in each of the dimensions. And then let's say that we're trying to decide what the regularization term would be for 2 separate models. So one model that uses w sub 1 as its parameters, and then a second model which uses w sub 2 as its parameters. So if we work through it, if we imagine just a linear models which is going to just take this weight matrix, or these weight parameters, and just apply it as a linear function of x, it turns out that in both these cases, by this particular choice of example x, both of these will produce the same prediction. So they'll produce the same output score. But it's not the case that the regularization will be the same. So if you work through it, it actually turns out that the regularization for this w sub 2 will be 0.25 squared plus 0.25 squared plus 0.25 squared plus 0.25 squared. So overall, that's 4/16, so that's 1/4. Whereas the regularization term for the w sub 1 is going to be 1 squared, which is 1. So the loss for the model that has these more spread out weights over the dimensions of the input is going to have a lower regularization term and correspondingly sort of be preferred based on this L2 regularization. So that's one way that you could think about trying to decide between different regularizers, is you can try to use your intuitive knowledge about what those regularizers will do in terms of the input dimensions to reason about which you might want to prefer. Because it turns out actually that in most cases, the L1 regularizer will do the exact opposite. It would prefer model parameters that are more centralized on a few dimensions of the input rather than spread out over all of them. So if you have some knowledge about your data, then you can potentially use your intuition about how the different regularizers will work on that data to decide between them. But in general, in practice, what I found is trying different regularizers tends to be what's used most commonly. So you can use some intuition, but guessing and then checking is, from a practical standpoint, quite effective as well. Okay, so now we have our more complete, we could say, loss function. So now we have this loss function L of W, so it's a function of our parameters, but also the data. And it's composed then of this data loss component, which is trying to encourage our model to actually fit to the training data, but also now this regularization component, which is trying to ensure that we don't overfit to the data and ensure that our final model, our sort of optimized model, still will perform well on the unseen test data. But now we have this question still of how it is we can find a good setting of the parameters so that we could achieve both of these objectives, right? So it'll perform well on the training set and hopefully also the testing set. And so that is where optimization comes into the picture. So the goal of optimization is summarized in this one function. So the goal is we want to produce some parameter set, W star, which minimizes this overall loss function, L of W. So we're going to take the argmin over this parameter set W of the loss function. So despite the fact that we've written it as this one equation, optimization is very, very difficult to achieve in practice. And so it's going to be a large topic moving forward for deep learning because it's quite computationally challenging to actually achieve. So to start out, though, let's try to build some intuition about how we can maybe think about optimization visually. So let's imagine that we're working within a 2D plane where along the x and the y coordinates, so it's kind of like along the horizon within this image, every point along that 2D plane would be a different parameter setting for our model. And the vertical elevation then along any of those points, which will fall somewhere on one of these cliffs, would correspond to sort of the loss or the fitness of our particular parameter setting along the plane. So the goal then we could think about for optimization is to say, given some starting location, right? So maybe some random location of an initial parameter setting, we then want to move downhill in terms of the loss, like loss combined with parameter space, to hopefully achieve at the lowest point, sort of the optimal model, right? So the model that minimizes the loss. This is ultimately the goal. So the first idea we could take, right, because we have to actually implement that concept in code, is we could do random search. So we could essentially just evaluate parameter settings randomly along that planar space, and then hopefully check that the loss function at each of those points is minimized. But either way, we'll check the loss function at every single one of those parameter settings and then take whichever parameter setting happened to have the lowest one. So implemented in code then would be that first strategy, which we would call random search. So you can see, so what we're doing is we're saying, like, initially our best loss is just some very large value. We're going to iterate for some discrete set number of times where we'll pick a random parameter setting. We'll then evaluate the loss at that specific parameter setting. And if this loss at this random setting is better than all the previous losses that we've seen, we'll say, oh, we found a new best parameter setting. And we'll just keep going through that until we run out of time, essentially, and then report at the very end the best overall value of the parameters that we found and the corresponding loss. The reason that this is bad is that it'll perform it'll be very, very slow, for one thing, right? Another problem is that assuming that we don't have an infinite amount of time, there's no guarantees that we'll ever find an optimal or even like a locally optimal solution using this approach. And so it's not used in practice. So one example, so there's like an experiment run here on the CFAR 10 data set where they tried, so as a reminder, that's the 10 category image classification data set with natural categories. So someone actually tried implementing this strategy and found that they could get like a 15.5% accuracy using the code that was shown on the previous slide, so like that set number of iterations. So this is not terrible, right? So it's not 0% accuracy, but to give a kind of a contrast, the state of the art right now in CFAR 10 is more than 95% accurate. So this random search is very, very far from the best performing models that we can achieve. So then the next idea that we might have is let's try and use some local knowledge about where our initial guess of a parameter setting is. And we'll use that local knowledge to hopefully iteratively improve the parameter setting over time. And the reason why you might sort of think, well, why can't like visually you can just see the lowest point in space? But on a computer, given some loss function that's non-convex, like a very complex loss function that's very, very high dimensional parameter space, not just 2 dimensions, our computers can't just sort of visually kind of like see the best parameter setting. They have to do very localized operations. And so the second idea is one that we're going to try and move towards, where we'll try and use just like this local knowledge to iteratively improve the parameter setting. And this is building up to really the approach that's used for state-of-the-art models, which is called backpropagation and gradient descent. So our idea is going to be to follow the slope in this second setting. And so to do that, let's first recall what it is a slope defines. So for a one-dimensional function, f of x, the derivative of that function from calculus gives us the slope of that function. So it's essentially the line that's tangent to the function at a specific point in space. And so mathematically, that's defined then as the limit of this finite difference, where you take you evaluate the function at some f of x, and then you take the difference of that value with f of x plus h. So it's some finite, very small step. And in the limit, as that step goes to 0, you'll arrive at the derivative of the function, so the true slope at that point. In multiple dimensions, we would extend this idea of a derivative to what we call a gradient. So a gradient you can think of as the vector of partial derivatives along each dimension of the input to our function. So assuming that the function is no longer just a one-dimensional input, but some n dimensions, you'll now have this n-dimensional vector. And so it turns out that the slope then, if you were to want to know the slope of, let's say, this multidimensional function along some given direction, you could take the dot product of that direction in the high dimensional input space with the gradient vector for that function at that point in space, and that would give you the slope of the function. And so we would call then the direction of steepest descent is the negative gradient. So what the gradient gives you ultimately, if it's the slope, it's the direction of steepest increase. So if you imagine taking the negative of that, moving in the opposite direction, you'll be guaranteed to move in the direction of steepest descent. And so this is going to be useful, right? Because connecting back to that idea of following the slope, if we imagine that we could calculate the gradient of this space, which is combined, like the loss combined with parameter space, we could then try to update our parameter vector using that negative gradient. So that is what's called gradient descent, and it's the algorithm that we'll be talking about as an approach to start training our models. So before we try and actually implement this in code, let's imagine walking through what the calculation for one of these gradients would be. So let's say that on the left-hand side of the slide, we have some current setting for a parameter vector w, and what we want to try and calculate, let's say, is the derivative of our loss function with respect to these weights. So we're going to try and calculate the gradient vector then on the far right. And so we're going to use this what we call numerically. So we're not going to calculate an analytical gradient here. We're just going to try and, using knowledge of the individual values on the far left and the individual loss function, let's say that's given to us, let's work through how we could use the finite difference method to actually calculate the gradient. So the first thing that we would do is, let's say that we want to calculate the term of the gradient vector along the first dimension of the parameter vector w. So what we would do using the finite difference method is we would take just that first dimension of our parameter vector, and we would take a very small step. So in this case, our step size, you can see, is 0.0001. All of the other dimensions in our parameter vector w are going to stay the same, but we'll reevaluate the loss function given this new, slightly modified parameter vector w. And then what we'll do is we'll apply the finite difference method to approximate the derivative of the loss function given this change in just the first dimension of the parameter vector w, right? So what we'll do is we'll take the loss for the modified version, like the stepped parameter, subtract from it the original loss, which was given to us here, divide by the step size, and then we arrive at our corresponding derivative, negative 2.5, and we would insert that into our gradient vector. So that's the first element of our gradient vector. Then what you would have to do is you would then have to go and do this same procedure for all of the other elements within your parameter vector to arrive at the full gradient vector, right? So then we would look at the second element of our parameter vector. We would apply a small step there, and we would reevaluate the loss given this slightly modified, just along one dimension parameter vector. We would again use the finite difference method to approximate the derivative along this dimension, and then we would have the second element of our gradient vector, 0.6. And then you would have to keep going through this. So this numeric gradient, we call it, has a couple of downsides, right? So if you kept going through all of the elements of your parameter vector and doing this process, you take a small step along one dimension, evaluate how the loss changes, and then approximate the derivative, you could arrive at an approximate gradient. But the downside is it's going to be very slow, right? So depending on how large your original parameter vector is, you're going to have then O of that many dimension steps to actually calculate one example of the gradient. And then the second is exactly that it is an approximate method. So this finite difference method depends on what your step size is, right? And so on a discrete computer, we cannot take the limit as the step size goes to 0. We have to pick some finite value for what the step size is, and then essentially like the level of approximation that we ultimately have depends on that step size that we're able to take. So what we would be interested in is a slightly better approach to evaluate these gradients, which we'll arrive at using analytical gradients. So let's say that we have some loss function. So here it happens to be the SVM loss function, which we talked about last time. And we also have some scores. We have some linear model defined to produce scores. What we want is for some given parameter setting w, we want to be able to calculate this gradient of the loss with respect to the parameter w. So that's how to read this math down here. So instead of using the numeric gradient method, which we saw would be slow and approximate, instead what we can do is we can use calculus and our knowledge of the particular parameterization of this loss function to actually directly calculate in analytic form, in closed form, what the gradient would be. So this will be much more efficient, and it will no longer be approximate. It'll be the exact calculation. So overall, what we can do is we can consider this gradient to be some function of the data and also the parameter setting w. So in practice, what we're going to do is we're going to, in the future, once we start working with more complex models, in particular neural networks and convolutional neural networks, we're going to be computing this gradient function using backpropagation. But that's not going to come until lecture 6. So just as a sort of a foreshadowing, what backpropagation will do, it's an algorithm that lets us calculate these gradients from sort of simple operations. So if you have some very complex function, so let's say that our loss function is itself a function of a convolutional neural network, which is very complex, backpropagation will give us an efficient algorithm to actually compute these gradients for a very complex function as a set of building blocks that increase in complexity. For today's lecture and for project 1, we don't actually need backpropagation because we're going to be working with much simpler linear models where we can, on paper, compute what the analytical gradients should be and then implement those without backpropagation. Okay, so actually let me take like a quick drink of water, see if there's any questions. Questions in the chat. Okay. So computing gradients. So there's two approaches that we looked at, right? So we saw that there's the numeric gradient. So it's nice in that it's for one thing, like it's nice in that conceptually it makes some geometric sense to us, right, in terms of trying to approximate that slope. But the downside is it's an approximate method, and also it's very slow. The analytic gradient, on the other hand, is exact. It'll guarantee that we get the correct gradient, the correct values for those gradient vectors. It's very fast, but it can be challenging sometimes to implement depending on the functions that we're trying to implement it for, because you actually have to derive on paper what the gradients should be before you implement them in code. So in practice, you're always going to be using the analytic gradient. So the nice part about PyTorch and TensorFlow and these machine learning frameworks is that they have built into them highly optimized backpropagation algorithms that will calculate these gradients for you. So in practice, you're always going to be using the analytic gradient. But having said that, if you're trying to implement your own gradient for some new like loss function that you might define for a research paper, sometimes deriving the analytic gradients on paper can result in some error. And so you'll want some way to sort of do a sanity check that what you've calculated on paper is actually correct. And so for that, the numeric gradient is still a very useful trick to actually check and make sure that the implementation you have is roughly in the range of what you expect your gradients to be. And so this is called a gradient check. So for project 1, in some of the helper function utilities, we've provided a function that will perform a numeric gradient check for you. So this will be a way for you to ensure that the analytic gradients you implement for those SVM loss function and the softmax loss function are roughly correct. But don't think that this is just for like the purposes of learning. In fact, actually in practice, PyTorch and TensorFlow, like they actually provide these same operations for doing numeric gradient checks because it's that useful to do in practice. So when you define some new loss function or some new neural network layer that has a complex analytic gradient to derive, it's actually in practice useful to check it numerically using some of these built-in functions. So we're going to get experience using some of these in project 1. And I'll also, so the other thing to point out, there's also a built-in function for PyTorch that would be able to do like sparse checking of second order gradients, like second order partial derivatives. So just, it is used commonly in practice. We're not going to be using that though for project 1. Okay, so now that we have, so there's these two ways that we could try to calculate a gradient. We could use the numeric method or we could use an analytic gradient. The next idea then is how it is we can actually use that gradient to update the parameters to start to improve the model's performance with respect to the loss function. And so the algorithm that we're using to actually do that is called gradient descent. So the idea here is we're going to iteratively move our parameter vector in the direction that corresponds to the negative gradient, which corresponds to the direction that will result in a decrease in the loss function. So in code, what that looks like is we have some initial parameter vector here, w. For some set discrete number of iterations, what we'll do is we'll calculate the gradient, and then we're going to subtract this gradient that we've calculated multiplied by some learning rate with our original or our preceding value for the parameter vector w. So within this code, the hyperparameters we have are first how it is we initialize our weight matrix, how it is that how many numbers of steps it is we take to perform this gradient descent. And then finally, the learning rate here, which corresponds to the step size that we're taking. Because you can imagine if you took too large of a step size, you might overshoot the minimum and potentially result in a worse parameter setting. So this learning rate is going to control the actual step size we're taking along this direction of descent. So visually then, it's useful to think about what this looks like. So in this plot, imagine that we have a two-dimensional parameter vector. So the vertical axis and then the horizontal axis correspond to different settings of the parameter vector along those two dimensions. And then the color, let's say, corresponds to the loss value at any of those given parameter settings. So let's say that the color red, which is sort of visualizing this center portion of the screen, let's say that's the smallest value of the loss, whereas these purples and these blues at the edges would then be like the highest values of loss. So the idea with gradient descent is if we take some initial point in this space and we take that to be our initial parameter setting, gradient descent is going to move this parameter vector stepwise along the direction towards the loss. And so for functions that are convex, we can guarantee the gradient descent, and also depending on the learning rate, but we can guarantee convergence to a global minimum. But in general, for the functions that we're going to be looking at in the future, so by functions I mean the loss functions that we're going to be looking at for our neural networks and our convolutional networks are not necessarily convex. So there's not a guarantee that this gradient descent is going to reach a global minimum, but it will, as long as our learning rate's small enough, it will at least descend to a local minimum. So visually what this looks like is, let's say, so this is going to be like an animation. So let's say we have some starting weight vector, which is visualized here. What gradient descent will do is it'll iteratively move that weight vector throughout the different steps of this algorithm until convergence or until the number of steps that you're taking sort of runs out. So at the end of gradient descent, we'll have some other parameter vector W, which will have moved within parameter space. And hopefully it'll be at a global minimum. Okay. So this idea then extended back to our notation for the loss function, it would be called batch gradient descent. So let's say that our loss function, as we've defined it in the past, is taken as the average over the full training set, right? So we have this 1 over n for the n training examples, and then a sum for each of those examples of the loss function for that particular example combined with the regularization term. So if we then imagine taking the gradient of this overall loss function with respect to our parameter vector, that's what we're referring to as batch gradient descent. So we're taking the gradient over all of the training examples within our training set. And so one downside with performing this batch gradient descent is that doing a sum over all the training set examples can be really expensive, right? So if you're working with ImageNet, for example, where there's 1.3 million images, just to get one gradient vector, which would let you take one step according to the gradient descent algorithm, you would have to do a sum over all 1.3 million images, right? Just to get one parameter update. So that's really, really expensive for large data sets. So instead of that, typically what's used in practice is a variant called stochastic gradient descent. And so the idea is, instead of having to take the gradient over the full sum for all of the training examples, let's just pick a random subset of the training set and take the gradient with respect to that subset. So instead of taking the sum over, let's say the full large N training examples, instead we might just pick 32 random training images or 64 random training images, and then calculate the gradient in the same way and use that as the update for our gradient descent algorithm. So what that would look like is shown then in this code. So we're still taking some initial parameter vector W, some discrete number of steps for descent, but instead of computing the gradient over the full data set, instead what we're going to do is take a mini batch, so some random sample from the data, compute our gradient using the mini batch, and then use that resulting gradient to update our parameter vector. So what we've done by doing this is we've introduced now a new set of hyperparameters. So we still have how it is we initialize weights as a hyperparameter, the number of steps that we're going to be doing this descent, the learning rate, but now what we've done is we've also added the batch size, so that could affect our final model's performance, and also how it is we sample these mini batches could affect our model's performance, right? So you'd imagine that if we uniformly randomly sample our training set, we might get a different model, final model performance, than if we were trying to sample the hardest examples from the data set, or if we were only sampling, if we were ignoring, for some reason, let's say 50% of the data set. Each of those different sampling strategies is also a hyperparameter that we would need to tune during model development. So as a sort of brief note, hopefully, so one interpretation of stochastic gradient descent is to now think of our loss function as actually an expected value if we're doing this random sampling. So if you treat the loss function as an expected value over your sampling strategy, then it turns out that you can also treat the gradient as an expected value over that same sampling strategy. So if you're interested in random variables and how the distribution of your sampling strategy can affect the gradients, this is kind of an interesting direction to look at. But in practice, we can just kind of work with the fact that the gradient is an expected value. We can perform this random sampling and still treat the approximation of that gradient as the sum over our discrete mini batch in practice. So, yeah. So one kind of pointer, one kind of useful web demo. Professor Justin Johnson created a really, really cool web demo of gradient descent in action. So it's linked in the PDF copy of these slides if you want to play around with it. It's really nice in that so you can change the individual parameter settings within a linear model. You can change the input data that's used to train it, and then you can visualize step by step how the model's predictions change throughout gradient descent. So it's useful to gain some intuition about how the algorithm will work for a simple like two-dimensional input space. So you can actually visualize the full input space. Okay, so we've defined now this training approach, and in theory it will work. Like in theory, we will move towards the minimum loss. The issue though is it's not perfect. So there's a few problems with stochastic gradient descent that it's worth thinking about. So the first one we could think about is like, so visualized on this example is imagine this as like sort of a two-dimensional contour plot of the loss function depending on where in a two-dimensional like vertical axis and horizontal axis parameter space you are. If we imagine that the loss function changes very rapidly in certain dimensions, so in this case it's changing very rapidly along the horizontal dimension of this parameter space, that would correspond to what we say is like the loss function has a high condition number, where that's defined as the ratio of the largest to the smallest singular value of the Hessian matrix. So the Hessian matrix is the matrix of the second order partial derivatives of the function. But the core idea is just imagine that this loss function changes very drastically in one dimension and in a very small degree in the other dimension. If we think about how stochastic gradient descent is going to actually be applied to this function, what it's going to do is it's going to take really, really large steps along the direction that has like a large change in the loss function, but very small steps along the direction where there's a small change in the loss function. And so correspondingly, it can actually produce very slow convergence properties that we might not want for training very complex models that have like a large number of parameters. So this is one issue with stochastic gradient descent that we're going to want to try and address. And so that's one. Another issue is imagine that our loss function is not convex and that it doesn't just have a single global minimum. Imagine instead that there's maybe many local minimum, or there's also saddle points where the gradient of our function is 0. So in those cases, what stochastic gradient descent is going to do if it falls into a local minimum or into a saddle point is it's going to stop converging at all, right? The model's not going to improve at all because the gradients are 0, and so the parameter updates are just going to keep it exactly where it's at. So this is yet another issue with the vanilla version of stochastic gradient descent, which we're going to want to try and address. Yet another potential issue with stochastic gradient descent, although this, as we'll see, might also be a benefit in some cases, is that by taking these random mini batches over as a subset of the overall training set and using those mini batches to define the gradient, our gradients now are going to be noisy. So to imagine what that might look like, this is just like a conceptual illustration. So if we have noisy gradients, we're not going to move along a smooth line now in parameter space using gradient descent. It's possible that we're going to perform a lot of computation that's actually moving us maybe away from the global minimum and not necessarily towards it because those random samples are not producing the true gradient, right? They're going to produce some, in all likelihood, not the exact gradient. And so this is yet another potential issue with stochastic gradient descent that we should think about when we're choosing which optimizer we want to use. So I just said that the stochastic gradient descent has this issue in that the random batches can produce noise in the gradient calculations, and as a result produce like these kind of noisy steps towards the global minimum or the local minimum. But in some ways that also could potentially be a benefit, right? Because imagine that we're at a saddle point and we're using batch gradient descent. Well, according to batch gradient descent, if we're at a saddle point, it's always going to produce the same gradient vector, which is 0, and we're never going to leave that saddle point. In contrast, if we're using stochastic gradient descent, if we've arrived at some saddle point, it's possible that the noise in stochastic gradient descent could sort of bump us out of the saddle point and then we could move back to actually converging towards a local minimum. So that noisy property of stochastic gradient descent, like it's potentially troublesome in that it'll probably result in slower convergence for like convex functions, but it's potentially beneficial in these cases where you have non-convex functions with saddle points. So this is an interesting thing to think about. Okay, so given these issues, let's try and think about ways that we could potentially address them. So there's been a lot of papers that look at taking this sort of vanilla stochastic gradient descent and modifying it to try and improve its performance for deep neural network training. So one idea that's been proposed that worked quite well is adding a momentum term to our function. So on the left-hand side here, this is the weight update equation using stochastic gradient descent that we looked at. So we're going to say like that the weight at the next time step is just going to be the current weight, and then adding to that the negative gradient at this, like given the current weight setting, right? So imagine then that we added what we call a momentum term. So what we're going to do is we're going to keep track of the velocity of our parameter vector in parameter space. As you can see here, the rho times the previous velocity plus the gradient at the current time step. And then what we're going to do when we update our parameter vector w is we're going to say that the weight vector at the next time step is the current weight vector moved by some scalar multiplied by this velocity. And so what we're sort of doing is like building up the velocity as this running mean, right? So we're like this is a running mean. And then in contrast, this rho we could think about as a sort of friction. So the rho is what controls like how much of the previous velocity we want to carry forward to the current time step. So if we think then about ways that this could potentially if we think about what this is sort of doing, we could imagine that maybe the gradient at some point within the parameter space is pointing along the horizontal direction, but if we have a velocity term associated with it, then this SGD with momentum is going to combine the two to result in a different parameter update than we would have got with just the vanilla gradient descent. And so, let me see. This is like a small note, just that sometimes when you're reading literature, you'll see SGD with momentum represented in different ways where the sign of the velocity update is flipped. They're actually like the same mathematically, so this is just like a small note. But what's more important to think about is how would adding this momentum term potentially solve some of those issues with stochastic gradient descent that we saw a few slides ago. So for one thing, if we have a loss function that has a local minimum, by adding the momentum term, it's possible that there could be a scenario where we have enough momentum that we would arrive at the local minimum during descent, but then we have enough momentum that it could potentially carry us out of the local minimum and keep on with convergence. So that's one issue. The same idea, like we could use like our physical intuition to imagine a saddle point where instead of reaching that point where there's a zero gradient, because we have this momentum, it can carry us forward and keep on converging. So there's two potential problems where the SGD with momentum could help us. Another, though, is that issue where, like with the poor condition number, let's say of our Hessian matrix, the momentum term could also sort of smooth out some of the steps that we're taking. So visualized in this like kind of conceptual diagram is like an imagination of what stochastic gradient descent might look like without momentum, versus if you add the momentum term, it'll sort of smooth out your trajectories. So in these cases where you would otherwise be taking very dramatic steps along some dimensions of space, momentum will tend to smooth out the steps that you're taking along those dimensions. Okay, so another note, I'm not going to spend too much time on this, but there are variants of how you would actually implement momentum for these purposes. So there's the sort of standard momentum update, which we just talked about, but also there's another variant called Nesterov momentum. I'll leave the slides, this is all included in the slides. So if you're curious about how you might change your implementation for momentum, you can certainly look at the slide material. But for our purposes, we're not going to be working with this implementation, and it's seen less frequently in the robotics literature. So it's an interesting concept if you're interested in how you can change your optimizers, but it's not something that we need to worry about for our use cases. Okay, so one optimizer, though, that we should worry about for our use cases is one that we'll see more commonly, which is called AdGrad. So this is now going to be trying to sort of, at a high level, trying to sort of adaptively scale what the gradient is for the different dimensions of our parameter vector. So it's sort of trying to handle, maybe that you could think about it like that case of the bad condition number. That's at a high level what it's going to do. So let's take a look at what what AdGrad does. So it's going to keep track of this term called grad squared, which is just it's a running total, it's a running sum of just the element-wise square for each of the elements within your gradient. And what it's going to use that for is within the parameter update for W, it's going to divide your overall parameter update by those squared elements, the square root of those squared elements running sum. And so what this is doing, we could think about it as it's treating this sort of like as a per parameter learning rate. So over time, as your AdGrad is running and you're accumulating value into this grad squared term, that's now going to affect how large of a step you can take for each of the elements within your weight matrix. And so, yeah, it's called like adaptive learning rates, and it's much more commonly seen than stochastic gradient descent. So typically, this can help with like I was saying, like those bad condition numbers, because what'll happen is if you have like a very, very large step along one dimension, what that'll do when you take the division, like when you divide by that large dimension, is it's going to reduce your ultimate parameter update for that dimension. So it tries to avoid your parameters taking like very, very large steps in some dimensions and small steps in others. In contrast, if your grad squared along a particular dimension was very small, like let's say less than 1, that would have a scaling term on your actual parameter update for that dimension and result in a larger step. So that's what we mean by like a per parameter learning rate. It's dynamically changing how big of a step you can take based on what the previous gradients were for each of those dimensions. Yeah, question? Right, it's trying to address some of the cons of the SGD optimizer. So the question was, does AdGrad try to address the cons of the SGD optimizer? Yeah. Yeah, so the question was, is SGD still preferred in certain cases to other optimizers, or how would we decide which optimizers are the preferred ones to use? So the choice of optimizer, ultimately, you could also think about as a hyperparameter. So a typical rule of thumb, so there's one that we'll look at called ATOM or ATOM W. Typically, those are the ones that are most frequently used in literature. As a good rule of thumb, it's not a bad idea to just start with vanilla SGD. If you want to check that your model is implemented correctly and that your loss is implemented correctly, and then to substitute other optimizers once you're sure that your model is set up correctly to see which of the optimizers produces like the lowest like overall loss or potentially the like highest cross validation accuracy. So the question was, if I'm getting good performance with a model using one optimizer and I'm getting bad performance with the same model but 3 other optimizers, then that's an indicator that my function is not generalized. Potentially, I think probably like the way I would interpret that scenario is to mean that the combination of the model parameters plus the data set, like plus the loss function, within that overall like very, very large space, the specific optimizer that you found has good final performance has some property, potentially like its ability to have adaptive learning rates, which allows it to get out of local minimum that the others are not able to get out of. Beyond that, I think it's very hard for me at least, to reason about, because the dimensionality of these spaces, when you combine like the parameters, like the dimensions of the parameter plus the dimensions of the training data plus the dimensions of the loss function, like reasoning about why it is that one optimizer is better than the others can be very difficult. Simplifying the problem, like simplifying the training set, might be one approach you could use to like start to visualize what the loss function is, but it's hard to say concretely in practice. So why we sum all historical weights within this function. So in other words, like why do we have this running total? You could think about it as in terms of why do we have that. So I mean, you could define an optimizer where you don't take the running total. That would be normalizing, yeah. If you don't have the running total, right, as being pointed out, that would just basically be normalizing the overall like norm of your gradient and result in,
I think they like to answer that.
yeah. Yeah, that would, but yeah, that would be normalizing your W's. I'm trying to think if that would be guaranteeing that it would move along a unit, like that might almost be like undoing the learning rate to some extent. Like you would just be moving along like a unit vector, like a vector of unit length in parameter space. Yeah. I think there was something else I wanted to add to the other question, but yeah. So AdGrad we'll see more. You'll probably see more frequently than stochastic gradient descent. So yeah. So one problem with AdGrad. So the good part is that the progress along these like very steep dimensions within the loss parameter space is going to be damped. So you're not going to have like those giant steps along certain dimensions and not others during convergence. And your progress along the flat dimensions will be accelerated by that division. But the problem is that it can be very slow over many iterations because you have this running total. So over time, what's happening is over time, this grad squared is growing and growing and growing. And so by dividing the overall parameter update by this growing and growing value, you're resulting in like the long running performance with smaller and smaller parameter updates. So potentially, if your number of steps is not sort of large enough for a given problem, you can eventually sort of converge with AdGrad before actually converging to a local minimum of the loss. So you can sort of stop performing steps at all because of this adaptive, because of the way that this adaptive parameter learning rate is implemented. Okay, so another idea to try and sort of fix that issue with AdGrad comes from an optimizer called RMS prop. So the idea here is to try and avoid that last issue. So what we'll do to try and avoid it is we'll introduce a decay rate to our running total. And so this decay rate will hopefully allow like our convergence to at least last longer. But it's possible that, like, once again, you could still have like convergence issues if your number of steps is too small. But RMS prop, once again, you'll probably see used in literature slightly more frequently than stochastic gradient, or than AdGrad, and certainly more frequently than just vanilla SGD. Okay, so that brings us then to Atom, which is one of the most commonly used optimizers. And the idea with Atom is it's going to try and combine the benefits that we get from momentum stochastic gradient descent with the benefits that we got from the adaptive like learning rates from RMS prop and AdGrad. And so the implementation of what is very close to Atom, if you want like the full details, the paper citation we have in the slides, is shown then in the code here. So what we do within Atom is we keep track of these two moments, like moment 1 and moment 2. And what we can think about is moment 1 is essentially representing the momentum term that we would have had from SGD plus momentum, whereas the moment 2 term is representing the per parameter like scaling of the learning rate that we got from RMS prop and AdGrad. There's like slight differences just in notation, but overall this is just trying to kind of combine those two concepts of momentum and adaptive learning rates per parameter. So one interesting kind of question, which I think for the sake of time I'll let you think about offline, is to think about what happens to these terms like at time t equals 1, and then you can assume like a beta 2 value of 0.999, and it can be, let me see, so like if you expand out like some of the thinking on this, some of the issue comes where like you might want to kind of like unbias some of these moments, because depending on the time step you're on, you can have some performance characteristics, but for the sake of time, I'm gonna move on. Atom is super common in literature. So this is just a sampling of papers from the past like 4 or 5 years that are from some of the top vision conferences in this case, but that use Atom. And what you'll find is that I think using Atom as like the first choice of an optimizer is not a bad rule of thumb, and then try others after Atom. What you can do then is start to compare some of the trade-offs that you get from these different optimizers. So they all have slightly different like kind of performance characteristics and sort of how they were intuitively designed. In this particular, like in this setting of like these 4 that we've chosen here, Atom satisfies all 4. But Atom's not guaranteed to always produce the best model. So because of this choice of optimizer is a hyperparameter, you'll likely have to, once again, try different optimizers to arrive at the best final model. A quick note in that, so sometimes you'll see references to L2 regularization, and then other times you might see references to weight decay. They're similar, but they're not exactly the same within regularization. So L2 regularization is exactly the same as weight decay if you have a stochastic gradient descent or stochastic gradient descent plus momentum, because you can imagine, so like up here where my cursor is, here's our loss function with L2 regularization. And if you imagine taking the gradient of this for the portion that is the regularization, after you've taken the gradient, you're actually going to arrive at the same 2 times the lambda plus the weight elements for stochastic gradient descent. But if you're using not stochastic gradient descent, then that's not going to be true. So when you take the gradient over some other loss function, these 2 won't be equivalent. So that's just a small note. Finally, then, so Atom is very, very common. Atom W, a slight modification to Atom, is the most common. So between Atom and Atom W, these are typically what you'll see for most papers that are coming out in literature. Sometimes you'll see a paper that just uses vanilla SGD, and typically what those papers will say is their contribution is maybe not on the optimal model, but so they were trying to use like the simplest optimizer, and they were still showing good performance, and then leaving it to others to further optimize with the choice of like maybe other optimizers. But so when you're starting out with some of the neural networks, trying Atom or Atom W is a good rule of thumb to start with. Okay, so now that we're at the end, so everything we've seen up to this point will be useful for implementing project 1 and then some of the future projects. And everything after this, we're not going to be actually implementing ourselves, but it's worth thinking about. So what we're going to talk about now is like if we were instead of using first order optimization, which is what we've been looking at, if we instead imagine using maybe more complex forms of optimization. So what we've looked at so far is all what we call first order, because we're taking just a derivative of this loss function and using that derivative to take steps that would minimize the loss function, right? So gradient descent. And so instead of that, though, what you could try doing is to use what's called second order optimization, where instead of trying to take just the slope of the loss function and descend along the negative of the slope, you could try and use a quadratic approximation for how the loss function is changing, and then step to minimize that approximation of the function. So it's a slightly higher order, it's like a higher fidelity approximation of how this loss function changes as you change the parameter vector. And one reason why this can be useful is what it can let you do is if you have an understanding about how the second order of this function changes, you could potentially take larger steps when you know that the gradient itself is not likely to change. So in other words, if at this portion of the space, the second order derivative of the function is small, that tells you that the gradient at this portion of space is going to change over, like as you change the parameter vector in a small amount, which could indicate that, okay, if the gradient is going to change a small amount, then I can afford a large step, or maybe a larger step I would have otherwise taken, because the gradient around this portion of space is going to stay the same. That's kind of the intuition. So you can sort of do this potentially like higher fidelity, kind of like adaptation about how big of a step size you're taking with a second order approximation. So in terms of how you would implement that, so you could approximate the loss function with a Taylor expansion, and then you could actually perform you could calculate a parameter update using like this equation that's shown on the slide here. One issue with this is that within this parameter update, you have to invert a Hessian matrix. So inversion of a matrix in general is going to be O of n cubed, and so if you have a really large number of parameters, this Hessian matrix is going to be massive. So in practice, this is hard to implement. There's approximate optimizers that have been implemented for you that you could use for this technique if you wanted to. Most commonly, what you'll see is LBFGS. And so this is an approximation because it doesn't actually store that full inverse. And so that's how it's actually able to be implemented in practice. So usually this can work, like this particular optimizer, it can work well when you have like the full batch, like a deterministic form of stochastic, or not stochastic gradient descent, but batch gradient descent. And usually it will not transfer very well to mini batch settings. And so kind of in summary though, in practice, Atom is usually the default choice, or sometimes Atom W. And then SGD plus momentum can sometimes outperform Atom, but you would likely have to tune like step size, learning rate, model parameters, and other choices, maybe like initial learning rate or initial model parameters and so forth. If you can afford to do full batch updates, you could try LBFGS, but otherwise, if you're planning on doing like mini batches, LBFGS usually won't work that well. And so overall, so in today's lecture, so we looked at kind of like a resummary of using linear models for image classification, and then looking at how it is we could start to optimize the loss function that we've defined for those models using gradient descent. And then we looked at variants of gradient descent, like stochastic gradient descent, and how variants of the optimizer could potentially affect the model's performance. So next time, what we're going to be looking at are neural networks, where we'll start to get into more complex models that can hopefully achieve higher classification performance for our next projects. And so with that, happy to stick around and take any questions, but I'll look forward to seeing you on Thursday.